There is a number that describes how fast the universe is expanding right now. It sounds simple. It should be easy to measure. And yet, the more precisely we measure it, the more it refuses to agree with itself. This number is called the Hubble constant. If our understanding of the universe is correct, every reliable method should give the same answer. Not exactly the same, but close. Within uncertainty, that is not what is happening. Instead, different methods give answers that are clearly separated. Not by noise, not by sloppy data. By margins large enough that cosmologists take them seriously. This is known as the Hubble tension. And the uncomfortable part is this. Both sides are using real data. Both sides are using mature instruments, and both sides keep improving, without converging. The Hubble constant describes how fast space itself is expanding. If two galaxies are far enough apart, space between them stretches, and they move away from each other. The farther away they are, the faster that separation grows. The Hubble constant tells us the rate of that expansion today. It is not just a detail. It sets the age of the universe. It affects how structures form. It shapes everything from galaxy evolution to dark energy models. Get it wrong, and something fundamental is missing. One way to measure the expansion rate does not look at the universe today at all. It looks back nearly 14 billion years. This method uses the cosmic microwave background, the afterglow of the early universe, emitted when the universe was about 380,000 years old. Satellites like Planck and ground experiments like ACTI measure tiny temperature patterns in this radiation with extreme precision. Those patterns encode the physics of the early universe. From them, scientists infer the expansion history, assuming the standard cosmological model. When they do this, they consistently get a lower expansion rate today, roughly 67 kilometers per second per megaparsec. The uncertainties are small. The data are clean. Independent teams using different instruments reach similar results. If the standard model is correct, this number should be right. The second approach stays in the nearby universe. Instead of looking back to the beginning, it measures distances step by step. This is called the distance ladder. It starts with objects whose distances we can measure directly. Then it uses brighter objects, like Cepheid variable stars, to extend that scale outward. Then it calibrates type Ia supernovae, which can be seen across vast distances. Once those supernovae are calibrated, scientists measure how fast galaxies are moving away and calculate the expansion rate directly. This method consistently gives a higher number, around 73 kilometers per second per megaparsec. Again, uncertainties have been reduced over time. The result has not drifted downward. Instead of converging, the gap has become clearer. At first, many assumed this would go away. Maybe the early universe model was slightly off. Maybe the distance ladder had hidden biases. Maybe telescope calibration errors were responsible. Years passed. Data improved. New instruments came online. The tension did not disappear. The early universe side gained support from independent measurements, including baryon acoustic oscillations from large galaxy surveys like DESI. The late universe side was scrutinized intensely. One of the biggest criticisms was that crowded star fields might bias distance measurements. Then, JWST entered the picture. JWST has sharper vision than Hubble and operates in infrared wavelengths that reduce dust and crowding issues. It was expected to either expose a flaw in the distance ladder or confirm it. What it did was more uncomfortable. JWST observations largely confirmed the previous distance measurements. They did not pull the expansion rate down to match the early universe value. This did not prove the higher value is correct, but it removed one of the easiest explanations for why it might be wrong. The gap remained. Other approaches have entered the discussion. Measurements based on the tip of the red giant branch tend to land slightly lower, closer to the early universe value, but not identical. Strong gravitational lensing time delays often fall in between, with larger uncertainties. None of these methods cleanly resolve the tension. Instead, they fill the space between the two main camps. The picture becomes more complex, not simpler. This is not about interpretation or preference. These are measurements of the same physical quantity. If they disagree, one of two things must be true. Either at least one method still has unknown systematic errors, or the standard cosmological model is incomplete. There is no third option. And that is why this tension matters so much. It is not speculative. It is not theoretical hand-waving. It is real numbers refusing to align. Some ideas try to modify the early universe. Extra energy components before recombination, changes to how fast sound waves traveled in the primordial plasma, slight alterations to dark energy behavior. Many of these ideas can ease the tension. Almost all create new problems elsewhere. No single proposal has emerged as a clean solution that fits all data. This is why cosmologists are cautious. The bar for changing the standard model is extremely high. The next few years will not deliver a single dramatic answer. Instead, they will bring more data. DESI will refine large-scale structure measurements. Euclid will map dark matter and lensing in unprecedented detail. The Roman Space Telescope will expand supernova and lensing samples dramatically. Each dataset will tighten constraints. Either the numbers will slowly move together, or the disagreement will harden into something impossible to ignore. Resolving statistical uncertainty is easier than proving systematics are gone. Each method has its own assumptions, calibrations, and weaknesses. As precision increases, small effects matter more. That makes fast resolution unlikely. This is why confidence is high that the tension is real, and low that it will vanish soon. If the tension survives, it will not mean we were wrong about everything. It will mean we were missing something subtle. And that is often how physics moves forward. Not with explosions, but with stubborn discrepancies that refuse to go away. The universe is expanding. We can measure it in multiple ways. And right now, the universe is telling us that our story is not finished. That disagreement is not a failure. It is an invitation.